Greetings, seekers of the unexplained, explorers of the hidden truth behind the veil of the everyday. From the deepest corners of the universe, from questions that both science and philosophy struggle to answer, the Quantum Observer invites you on a journey today. A journey that will not only reveal the wonders of physics, but also challenge you to question the very essence of your existence. What if the reality we perceive is nothing more than a meticulously crafted illusion, a complex symphony of code and data designed for us to experience it as tangible, as undeniable? Brace yourselves, because from this moment, your perception of the universe and of yourself may never be the same. Imagine for a moment that the chair you're sitting on, the air you breathe, the screen illuminating your eyes right now are mere projections. Perfect projections. Yes, so convincing that your entire life you've believed in them with blind faith, yet projections nonetheless. It's a thrilling yet terrifying idea, isn't it? An idea that has fascinated thinkers, scientists, and dreamers for centuries, and today resonates eerily with the latest discoveries in quantum physics and cosmology. What if reality, this vast and complex experience we call life, is essentially a simulation? A simulation so sophisticated, so incredibly detailed, that it is indistinguishable from what we've always assumed as real. We're not talking about cheap science fiction. This is a serious mathematical and physical possibility, debated in the halls of the world's most prestigious universities. If you seek answers to the deepest questions of existence, if you dare to look beyond the obvious, then this is where those answers begin to unfold. And if, by the end of this journey, you feel as intrigued and awed as we do, I invite you to subscribe to the Quantum Observer and join our growing community of curious minds, the most effective way to support us and continue exploring the greatest mysteries of the cosmos together. Now, let us dive deeper into this unsettling idea. For millennia, humanity has clung to the notion of an objective reality, a world existing independently of our perception. We believe the stars shine even if no one watches, that mountains rise majestically even without eyes to behold them. But what if this belief is naive? What if this apparent solidity is just a facade, an interface brilliantly designed for our minds? Think about it. How could you distinguish reality from a perfect simulation if everything you see, hear, touch, and feel is programmed to be perfectly coherent? The truth is, you probably couldn't. This is not a new concept. From Plato's cave to the sacred texts of ancient civilizations, the idea that our reality might be an illusion has echoed throughout history. But what was once philosophical reflection now carries an unsettling scientific nuance. The very physics that allows us to understand the universe is now whispering that perhaps, just perhaps, everything is a construct. How do we arrive at this radical conclusion? The clues lie in the most abstract depths of quantum mechanics, in the fine-tuning of cosmological constants, and even in the way information appears to be a fundamental component of the universe itself. Imagine a vast computer program so immense it spans entire galaxies, stars, planets, and yes, every one of us. A program operating with unprecedented precision, simulating every atom, every interaction, every thought and emotion. For the inhabitants of this simulation, experience would feel as real as what you are living right now. They would have no way of knowing they exist inside a digital construct because the laws of their simulated universe would be internally consistent, their memories implanted, their perceptions generated by code. This is the essence of the simulation hypothesis. And it is not just a flight of imagination. It is a serious proposal rigorously developed by scientists and philosophers such as Bostrom. But why would anyone or anything create such a vast and complex simulation? The motivations could be infinite and beyond our understanding. It might be a scientific experiment by a far more advanced civilization, a way to relive the past explore possible futures, or simply a pastime of a superior intelligence. Perhaps we are the product of an ancient simulation, remnants of civilizations that reached technological heights, capable of generating entire universes within their computers. The idea may sound fantastical, like a science fiction movie, but remember, only decades ago, the idea of carrying a device to talk to anyone across the world, access all the information on the planet, or watch videos of cats would have seemed like pure magic. Now, it's normal. Technology advances at astonishing speed, and what seems impossible today could be routine for a civilization billions of years more evolved. We face a fundamental question: how can we know if what we experience is true reality or a simulation? The short answer is, it's extremely difficult, if not impossible, with our current means. A simulation would, by definition, be designed to deceive. Yet there are peculiarities in the laws of physics, anomalies, and astonishing coincidences that hint at the computational nature of our existence. Physical constants, for example, are fine-tuned with precision that defies chance. If any were slightly different, the universe and life itself would not exist. Is this pure luck, or a deliberate fine-tuning as if by a programmer ensuring the simulation functions? This is the starting point of our journey, a journey through quantum mysteries, cosmological paradoxes, and philosophical implications, suggesting that reality may be far more malleable, far more programmable than we ever imagined. We are not here to instill fear, but to open our minds to the most astonishing possibilities science offers, to awaken to the idea that existence is stranger, more wondrous, and perhaps more artificial than our intuition allows. Prepare your minds to be expanded, for what comes next will only deepen this unsettling question: if we are indeed part of a simulation. Some interpretations suggest that it is quantum decoherence, the interaction of a quantum system with its environment, that causes the collapse of superposition, not necessarily consciousness. However, even in that case, the idea that information manifests differently depending on how it is interacted with remains highly compatible with a programmed reality. The observation paradox is undoubtedly one of the most challenging ideas science has offered us. It forces us to look at our role in the universe with new eyes. Are we passive receivers of a pre-existing reality, or active creators of a universe that takes shape as we observe it? If we are the latter, and if this creation is mediated by the rules of quantum mechanics, then the line between reality and simulation becomes incredibly blurry. In the stillness of this revelation, the question resonates strongly. If our observation is the rendering of the universe, who is the programmer that set the rules to make that rendering possible? And are we part of the code ourselves, or are we the conscious players within this vast cosmic game? This is only the beginning of a series of questions that intertwine with the most unsettling possibility of all: that what we want to see, touch, and feel is merely a beautifully crafted user interface. Chapter 4: The God Particle and the Cosmic Matrix, Threads of a Simulation. Welcome back to the Quantum Observer, your portal to the deepest mysteries of the universe. We have already explored the unsettling idea of the simulation and the surprising activity of the quantum vacuum, as well as the observation paradox that makes us question whether we are mere spectators or active participants in the creation of reality. Today, we are going to unravel the mystery of one of the most famous and elusive particles in modern physics: the X boson, often known as the God particle, and its relationship with the X field. Prepare yourselves, because what we discover about this fundamental particle could be a crucial thread in the fabric of a cosmic matrix. Since childhood, you have been taught that mass is an inherent property of matter, that a pencil has mass because it is a pencil, and a car has mass because it is a car. But particle physics tells a far more fascinating and strange story. Most fundamental particles, like electrons or quarks that form protons and neutrons, are actually incredibly light, and some, like photons, have no mass at all. So where does all the mass we observe in the universe come from? What gives particles their substance, their weight? This is where the X-field comes into play. Imagine the entire universe immersed in an invisible, omnipresent field, as if everything were submerged in a vast ocean of cosmic molasses. This is the X-field. As particles move through this field, they interact with it, experiencing a kind of resistance, a form of friction. The more strongly a particle interacts with the X-field, the more mass it acquires. Particles that do not interact at all, like photons, have no mass and travel at the speed of light. Those that interact weakly, like neutrinos, have a small mass, and those that interact strongly, like quarks, acquire considerable mass. The X boson is the manifestation of this field. It is like a wave or excitation in the X field, similar to how a photon is an excitation in the electromagnetic field. Its existence was predicted more than half a century ago, but was only experimentally confirmed in 2012 thanks to the Large Hadron Collider, LHC, at CERN. It was a monumental moment for science, validating the standard model of particle physics, our most complete theory of how fundamental particles and the forces that govern them work. Now, how does this transcendental discovery connect with the hypothesis that the universe is a simulation? Think of the X-field as a kind of underlying code that gives properties to objects in our universe. If reality were a computer program, the X-field could be interpreted as an initialization function or a property assignment algorithm. This algorithm is what assigns mass to particles as they interact with it. Particles do not inherently have mass. They acquire it by passing through this omnipresent field in a simulation. Every object in the virtual world has a set of properties defined by the code: its color, texture, elasticity, and also its mass or virtual weight. The X-field and its associated boson could be the implementation of an efficient mechanism to assign this fundamental property to all particles. Instead of coding mass individually for each type of particle, the programmer simply defines a field that, through its interactions, dynamically and uniformly confers this property to the entire simulated universe. It is an elegant and economical solution in programming terms. Moreover, the fact that the X-field has a non-zero vacuum value, meaning it is active everywhere, even in what we consider empty space, adds another layer of fascination. It is not a field that switches on or off. It is always present, always interacting. This makes it a fundamental pillar for the stability and very existence of matter. Without it, atoms could not form, stars could not shine, and life as we know it would be impossible. This fine-tuning of the X-field is one of many cosmic coincidences that some interpret as hints of an underlying design. In essence, the God particle is the piece that completes the standard model puzzle, allowing all other particles to make sense and acquire the mass necessary to form complex structures. If this boson is the key to mass, and mass is the key to the existence of matter, then the X-field, in a way, is the matrix that sustains material reality, the essential gear that gives weight and shape to everything around us. Here comes the deeper reflection. If the universe is a simulation, then the laws of physics are simply the coded rules of the game. The X-field, as the mechanism that gives mass to matter, is one of the most fundamental rules. It is not just a property of matter, but a universal interactions mechanism that defines how fundamental particles behave and group. This type of universal mechanism is precisely what we would expect to find in an efficiently programmed system. The existence of a God particle permeating the cosmos, granting mass to matter through its interaction, resonates powerfully with the image of a universe that is, in essence, a vast and complex piece of software. It leads us to ask, who designed this field? Who set the parameters so that particles acquire precisely the mass necessary for stars, planets, and ultimately conscious life to emerge? This enigma pushes us to look beyond mere scientific description and consider the philosophical implications. The X-field is not just part of physics, it is an integral part of the structure of our reality. If it is the matrix that bestows mass, and mass is a requirement for the existence of objects and beings, then the existence of this field connects us directly with the foundations of our being, and perhaps with the master code that defines everything. At the core of matter, in the secret of what gives us weight and shape, we find another clue. A clue that, like a golden thread, intertwines with the disturbing possibility that this vast and wonderful universe, with all its finely tuned laws and constants, is actually the product of an intellect, a designer, a programmer. The God particle speaks not only of physics, but of metaphysics, the possibility that the universe, at its deepest essence, is a quantum simulation. Chapter 5. The Holographic Principle. We live in a three-dimensional illusion. Welcome, truth explorers, to a new journey with the quantum observer. We have unraveled the possibility of a simulated reality, the vibrant activity of the quantum vacuum, the observation paradox that makes us co-creators, and the fundamental role of the God particle in assigning mass. Today, we dive into one of the most radical and fascinating ideas in theoretical physics, the holographic principle. Prepare yourselves, because this concept suggests that the universe as we know it might be a gigantic projection, a three-dimensional illusion derived from information encoded on a two-dimensional surface. Imagine watching a 3D movie. You perceive depth, volume, and movement. But in reality, that 3D image is projected from a 2D screen. It is an illusion, a reconstruction of flat information that our brains interpret as depth. Now, scale that idea up to the cosmos. What if our vast three-dimensional universe, with all its galaxies, stars, planets, and each one of us, were actually a holographic projection? The holographic principle arises at the intersection of quantum gravity and black hole thermodynamics. It was first proposed by physicist Gerard T. Hooft and later developed by Leonard Susskind and Juan Maldacena. The central idea is that all the information contained in a volume of three-dimensional space could be encoded on a two-dimensional surface at its boundary. It is as if the universe were a gigantic hologram where the information of the three-dimensional image is stored on a 2D plate. The inspiration for this idea comes from black holes. Stephen Hawking and Jacob Bekenstein demonstrated that black holes have entropy, a measure of disorder or information. And surprisingly, this entropy is not proportional to the black hole's volume, as one might expect, but to the surface area of its event horizon. This is extraordinarily counterintuitive. Think of a hard drive. The amount of information it can store is proportional to its volume, not its surface. But in black holes, information appears to be imprinted on the surface. This revelation led to a bold conjecture. If the information of a black hole, a three-dimensional object, can be encoded on its two-dimensional surface, could this principle apply to the entire universe? Could the information of our three-dimensional universe be encoded on some kind of distant boundary, like a gigantic cosmic projector? This means that what we perceive as three spatial dimensions could be a reconstruction of data residing in a fundamentally two-dimensional reality. To understand better, think of a credit card with a hologram. The image on the hologram appears to have depth, but in reality, all the information is recorded on a flat surface. The holographic principle suggests our universe is analogous to this. What we experience as depth, distance, and volume could be an illusion generated from more basic, flat information at the edge of our universe. Here is where the connection to the simulation hypothesis becomes profoundly unsettling. If the universe is a hologram, then by definition, it is a projection, and a projection is inherently a form of simulation. In a simulated universe, the most efficient way to store and process data could be in a lower dimension, then render the three-dimensional experience for the observing players within the simulation. The complexity of a 3D universe would be immense for a supercomputer, but if only 2D information storage is needed and then projected, the computational load would be drastically reduced. Imagine a virtual reality video game. Everything you see and experience in the 3D virtual world is generated by data stored in a computer system that, at its most fundamental level, is two-dimensional: chips, circuits, screens. The holographic principle suggests that the relationship between our universe and its foundation could be similar. It is not that we are literally inside a computer in the traditional sense, but that the laws of physics governing our universe behave as if essential information were encoded on a 2D screen. This idea is not only fascinating but also offers solutions to some of the deepest problems in physics. For example, it helps reconcile general relativity, which describes gravity in the large-scale universe, with quantum mechanics, which describes the small-scale world. In string theory, one of the candidates for a theory of everything, there exists a correspondence called the AD-CFT correspondence, a concrete realization of the holographic principle. This correspondence suggests that a universe with gravity in a particular space-time, anti-de Sitter space, ADS, is mathematically equivalent to a quantum field theory without gravity in one fewer dimension, CFT, conformal field theory. In simpler terms, it is as if a three-dimensional universe with gravity could be perfectly described by a two-dimensional universe without gravity. This does not mean we are literally living on a 2D surface. It means that the information needed to describe our 3D universe could be encoded in a way mathematically equivalent to a 2D description. It is a way of saying that reality is far more abstract and less solid than it seems. If information is the fundamental component, and that information can be compressed or projected, then the idea that we are a simulation becomes even more plausible. The deepest implication of the holographic principle is that the reality we perceive, with its depth and volume, could be an interface, a generated interface for our senses so that we can interact with it. It is as if the universe were a gigantic monitor, and what we see is the image, not the source code behind it. This perspective forces us to reconsider the nature of existence itself. If we are projections, who is the projector, and what exists on the fundamental screen where the original information resides? In the stillness of this revelation, the question resonates powerfully. Is our existence a sophisticated illusion, a three-dimensional projection of two-dimensional code? If so, reality is a book that opens as we observe it, and each page is written in a language we are only beginning to decipher. The holographic principle is not just a theory. It is an invitation to look beyond the veil of the apparent, to question the solidity of what we think we know, and to prepare for the most astonishing possibility of all, that we are shadows in a cosmic cave, shadows that can, with the help of science, glimpse the light that projects them. Chapter 6. The discreteness of space-time. Pixels in the cosmos greetings, seekers of hidden truths, and welcome once again to the quantum observer. We have navigated the simulation hypothesis, the bubbling quantum vacuum, the observation paradox that makes us co-creators, and the astonishing holographic principle suggesting our reality is a projection. Today, we delve into one of the most radical, yet intuitive, ideas if we consider a simulated universe: the discreteness of space-time. Prepare yourselves, because this notion suggests that the very fabric of the cosmos could be composed of minimal units, like pixels on a giant screen. A clear sign that we might live inside a universal-scale computer program. Since we learned to perceive the world, We have assumed that space is continuous, that any distance can be divided into infinitely smaller parts, and that time flows smoothly and uninterrupted. This is the basis of classical physics, where equations operate with variables that can take any value, however infinitesimal. But quantum mechanics and theories that seek to unify it with gravity whisper a different story. A story where space and time are not fluid, but have a granular structure, a kind of quantization. Imagine looking at an image on a digital screen. From a distance, the image appears perfectly smooth and continuous. But if you zoom in far enough, magnifying the image repeatedly, eventually you start to see the individual pixels, the small squares that compose the image. Suddenly, what seemed continuous is revealed as discrete, made of fundamental units. The idea of space-time discreteness suggests that our universe could be the same. If we could zoom in closely enough, we would see the pixels of space and the ticks of time. These minimal units are known as the Planck length and Planck time. They are scales so incredibly small that they defy imagination. The Planck length is approximately 1.610 to 351.6 r times 10 times 35 and 1.610 to 35 meters, a number trillions of times smaller than an atom. The Planck time, the time it takes light to travel that distance, is approximately 5.410 to 445.4 answers times 10 for 445.410 to 44 seconds. At these scales, our current laws of physics break down, and space and time are believed to cease being continuous, becoming something fundamentally granular. Why is this relevant to the simulation hypothesis? Think about it. In any digital simulation, no matter how sophisticated, there's always a minimum resolution. A video game has pixels, a flight simulator has a refresh rate, a 3D modeling program has vertices and polygons. Infinite information cannot be simulated on a finite system. If our universe is a simulation, then the existence of minimal length and time, the impossibility of dividing space and time beyond a certain point, would be an inescapable signature of its computational nature. They would be the pixels and frames of the cosmos. Quantum gravity theories, such as loop quantum gravity or certain versions of string theory, suggest that space-time is not a smooth background where events occur, but a dynamic network of space-time atoms. These theories propose that space itself is quantized, not infinitely divisible. If this is true, it would mean that reality at its most fundamental level is not analog but digital. Imagine the universe as a gigantic algorithm. For that algorithm to function efficiently, it cannot operate with infinite data points. It needs discrete units to work with. The Planck length and Planck time would be precisely those units. They would be the bits and ticks of the cosmic supercomputer clock that run our reality. When we observe the universe at macroscopic scales, its granularity is imperceptible. Just as we don't see the pixels on a high-resolution screen from a normal distance, at the most fundamental scales, the discrete structure would be revealed. This could also explain why the speed of light is a universal constant in a simulation. The speed of light might be the system's processing limit, the maximum speed at which information can propagate through the network of spatial pixels. It's not that light has an intrinsic maximum speed, but that it's the maximum allowed by the game engine running the simulation. The idea of space-time discreteness also aligns with the concept of information as fundamental. If the universe is information, that information must be stored and processed in discrete units. You cannot have an infinite amount of information in a finite volume. Planck units would be the information quanta of the universe. Each pixel of space-time could hold a finite amount of information, and the reality we experience would be the manifestation of that information. Think of glitches or errors sometimes observed in video games. Sometimes an object passes through a wall or a character levitates inexplicably. These are mistakes in the code or rendering. If space-time is discrete, could there be glitches in our own reality? Some unexplained phenomena, like dark matter and dark energy, or even certain anomalies in the cosmic microwave background radiation, have been speculatively linked to possible errors or limits in the simulation. While these ideas are highly speculative, the notion of discrete space-time gives them a conceptual framework. The search for quantum gravity is, in essence, the search for the resolution of our universe. If we find it, and if that resolution is finite, then evidence of a simulation would become even more compelling. Not only would we be living in a universe with physical laws resembling algorithms, but in a universe with a fundamental structure akin to a computer program, from the vast expanse of the cosmos down to the tiny quantum scale. The question persists. Is the universe an analog artwork, infinitely detailed and continuous? Or is it a digital masterpiece built from the smallest pixels physics can conceive? The possibility of discrete space-time invites us to view reality with new eyes, to see the fabric of the cosmos not as a seamless cloth, but as a tapestry woven from threads of information, each a testament to a possible cosmic matrix. It's a concept that, while unsettling, opens us to a level of wonder that transcends our usual understanding of existence. Chapter 7. The Universe as an Information Processor. Bits of Existence. Greetings, travelers of knowledge, and welcome once again to the Quantum Observer. We have unveiled the unsettling hypothesis that reality could be a simulation, explored the quantum vacuum as a sea of potential, and confronted the paradox of observation and the holographic principle. We have also considered the possibility that space-time is discrete, with cosmic pixels suggesting a digital structure. Today, we will delve into an idea that connects all these concepts, the notion that the universe is not just matter and energy, but also information. Get ready, because this perspective suggests that physical processes and cosmic evolution could be interpreted as massive computational operations, transforming data into reality. For centuries, physics focused on matter and energy. We believed the universe is made of particles interacting via forces, and these interactions give rise to everything we see, from the tiniest atoms to the largest galaxies. But as physics has advanced, especially with the advent of quantum mechanics and information theory, a new and radical perspective has emerged. Information is not just something that things have. It could be the fundamental substance of reality. Imagine a book. A book is made of paper and ink, matter. But its true value, what moves, teaches, or entertains us, is the information it contains, encoded in words and sentences. Similarly, some physicists, like John Wheeler, suggested the famous phrase, "it from bit." From the bit emerges the it. This phrase encapsulates the idea that physical existence, the it, emerges from information, the bit. It's as if the universe is not merely a collection of things, but a vast collection of binary yes or no questions answered at every moment. Think about it. Every elementary particle, every interaction, every state in the universe can be described with information. An electron's position, its spin, its charge, all are bits of information. When two particles interact, they exchange information. When a system evolves, it is processing information. From the formation of stars and galaxies to the evolution of complex life, the universe has been a gigantic, continuous information process. Consider thermodynamics. The second law, which states that entropy, the disorder of the universe, always increases, can also be interpreted as an information principle. A disordered system is one where information is more dispersed, less organized. The arrow of time, always moving toward the future, could be the arrow of information moving toward higher entropy states. How does this vision of the universe as an information processor relate to the hypothesis that we are a simulation? If the universe is, in essence, processed information, then it is inherently computational. A computer, by definition, processes information. If reality is a constant flow of bits being organized and reorganized according to certain rules, then the universe is effectively a massive computer. In a digital simulation, everything reduces to bits manipulated by algorithms. Objects, physical laws, interactions, consciousness, everything is represented as data and functions. The idea that the universe is an information processor means we are already speaking the language of computation. The laws of physics are the algorithms, particles are the variables and states, and the evolution of the universe is the execution of those algorithms. Even phenomena like the formation of cosmic structures, galaxies, galaxy clusters, can be seen as computational processes. Small fluctuations in matter density in the early universe, which are information about the initial state, get amplified over billions of years via gravity, computing the formation of large-scale structures, the evolution of stars and planets, and the complex chemistry leading to life. Everything can be interpreted as a series of intricate calculations. Life itself, with DNA as its universal information carrier, is a testament to this principle. DNA is a code, a program executed to build and maintain an organism. Biological processes are, in essence, molecular computations. Our brains, with their neural networks and complex patterns of electrical activity, are the most sophisticated information processors we know. If life on Earth is a form of information processing, why wouldn't the entire universe be? If the universe is a computer, the question arises, who built it or who programmed it? The answer is not simple and takes us to the doors of metaphysics. But the mere fact that this is a valid question in the framework of modern physics is astonishing. We are no longer talking about a machine of gears and pulleys, but a system operating with the logic of information. This perspective also addresses efficiency. If an extremely advanced civilization wanted to create a universe simulation, it would not build physical hardware for every atom. Instead, it would encode the fundamental rules of information and allow the computation to unfold. The computational efficiency of our universe, the way its laws seem optimized for complexity and emergence, could be a sign of design. At the heart of this idea is the profound implication that reality is not static, but a dynamic process of computation. It is not a fixed painting, but a continuous rendering. And if the universe is processing information, then every time we experience something, every time we think, every time we interact, we are in a way participating in that vast cosmic computation. Thus, the distinction between hardware and software, between the physical and the informational, becomes blurred. If the universe is an information processor, then we, with our conscious minds processing information on a microscopic scale, are an intrinsic part of that machine. We are the bits in motion, the calculations being executed. And in this grand symphony of data and algorithms, reality unfolds before us. A digital mystery we have only begun to decode. Chapter 8. Unexplained Phenomena, System Failures or Cosmic Glitches. Greetings once again, observers of the extraordinary, and welcome to the Quantum Observer. We have journeyed through the unsettling hypothesis that reality is a simulation, explored the bustling quantum vacuum, marveled at the observation paradox and holographic principle, and considered the universe as a vast information processor with possible space-time pixel. Today, we will focus on something even more unsettling, the unexplained phenomena that populate our cosmos. Could these anomalies, these mysteries that conventional science struggles to unravel, be what, in the language of computing, we call system failures or cosmic glitches? Think of a very complex video game, a realistic open-world simulator with photorealistic graphics and impeccable physics. Even in the best games, strange things happen. A character gets stuck in a wall, an object floats inexplicably, or a texture flickers oddly. These are glitches, imperfections in the code or rendering that reveal the artificial nature of the environment. And if our universe, with all its apparent perfection, also had its own glitches on a cosmic scale, one of modern cosmology's greatest enigmas is dark matter and dark energy. Together, they make up approximately 95% of the universe's content. Yes, you heard that right. 95% of what exists in the cosmos is something we cannot see, touch, or fully comprehend. Dark matter is an invisible substance exerting the gravitational pull necessary to explain how galaxies rotate and how galaxy clusters stay together. Without it, galaxies would disintegrate. Dark energy, on the other hand, is a mysterious force accelerating the universe's expansion, pushing galaxies further apart at an ever-increasing rate. The existence of these two entities is inferred from their gravitational effects. We haven't detected them directly, despite decades of intensive experiments. To a cosmic programmer, dark matter and dark energy could be placeholder code or hidden variables necessary for the simulation to function correctly. They are like behind-the-scenes adjustments that make the physics of the simulation align with expected outcomes without requiring the players of the simulation to understand or see them directly. They are patches or modifications made to the original code so that the universe evolves in the desired way. Another potential glitch is found in the physical constants, fundamental numbers governing the laws of our universe, such as the strength of gravity, the mass of the electron, or the speed of light. Remarkably, these constants are fine-tuned with astonishing, almost miraculous precision, allowing stable stars, complex elements, and ultimately, life to exist. If any of these constants were slightly different, the universe would be vastly different, and life could not exist. This is known as the anthropic principle. For many, this fine-tuning is one of the strongest pieces of evidence for underlying design. In the context of a simulation, fine-tuning wouldn't be a fortuitous coincidence, but the work of a programmer who calibrated the system parameters to achieve a specific outcome, a universe that hosts conscious observers. These would be lines of code carefully adjusted to make the universe program run smoothly and produce the desired results, like a game designer tweaking the physics to make gameplay fun and exciting. Consider also the anomalies in the cosmic microwave background, CMB, the afterglow of the Big Bang, a snapshot of the universe when it was only about 380,000 years old. Scientists have observed strange patterns, such as the cold spot or anomalous alignment of large-scale features, which don't perfectly match standard cosmological predictions. For some, these could be simulation artifacts, small errors or limitations in how the universe was rendered in its early stages. It's as if the rendering resolution wasn't perfect everywhere, leaving tiny imperfections visible only with the most sensitive instruments. And what about the Fermi paradox, which asks, if intelligent life is common in the universe, where is everyone? Despite the cosmos' vastness, we have found no evidence of advanced civilizations. In the simulation context, a possible explanation is that other civilizations simply aren't programmed into our simulation, or the computational resources to simulate them are too high, or we exist in a level or instance of the game where only our part is simulated. It's an eerie silence that could be the result of code optimization. Even the limits of physics, like the speed of light, could be seen as system failures or constraints. If light cannot travel faster than a specific speed, it's because the hardware or software of the simulation imposes that limit. It's not an intrinsic physical law, but a computational restriction, a kind of bandwidth limit for the propagation of information within the simulated universe. These unexplained phenomena, which keep us awake at night and push scientists to the edge of their ingenuity, take on new meaning under the lens of the simulation hypothesis. They are not merely mysteries to solve, but possible clues. They are like loose threads in a tapestry. When pulled, they could reveal the underlying structure. Each anomaly, each finely tuned constant, Each inexplicable absence could be a fingerprint of the programmer, a signal that what we experience is, in fact, a program. The idea is disturbing, yes, because if these are glitches, system failures, the implication is that there is a designer, a creator, or at least an executor of this simulation. It forces us to go beyond purely materialistic explanations and consider an intelligence outside our immediate perception. The universe is full of wonders, but also enigmas that, in their persistent resistance to explanation by known laws, invite us to the most radical possibility of all, that these are not failures of nature, but errors in the code of reality. Chapter 9. Nick Bostrom's Simulation. Hypothesis. The most disturbing argument. Welcome back, tireless seekers of truth, to the Quantum Observer. We have explored the intriguing idea that we are a simulation, quantum vacuum fluctuations, the observation paradox implicating us in reality creation, the holographic principle projecting our universe, possible space-time pixels, and cosmic glitches suggesting an underlying matrix. Today, we will break down one of the most influential and disturbing arguments for the simulation hypothesis presented by Swedish philosopher Nick Bostrom. Prepare yourselves, because his logic is so powerful that the probability we are in a simulation could be surprisingly high. In 2003, Nick Bostrom, a philosopher at the University of Oxford, published a seminal essay titled, "Are You Living in a Computer Simulation?" In this paper, Bostrom does not argue that we are definitely in a simulation, but that at least one of three propositions must be true. It is a trilemma, a logical statement forcing us to confront uncomfortable realities. The basis of Bostrom's argument is as follows. He assumes that over time, the computational capacity of advanced civilizations, at least some fraction of them, will become so immense that they could create simulations of reality indistinguishable from reality itself. Think about it. If technology continues to advance at the current pace, or even faster, it's not hard to imagine a future where supercomputers can simulate entire universes, including conscious minds. Once we accept this premise of future technological capability, Bostrom presents three interconnected propositions, one of which, according to his logic, must be true. It is almost certain that technologically mature civilizations do not reach the post-human stage. This means it is extremely unlikely that a civilization will reach a technological level capable of running simulations of conscious ancestors. Why wouldn't they reach it? Perhaps most civilizations self-destruct with their own technologies, are annihilated by cosmic catastrophes, or simply lose interest in technological progress. It is a pessimistic view of intelligent life's future, a warning that the great filter preventing the proliferation of advanced life may still lie ahead. If true, it implies that the path to advanced simulations is blocked by an insurmountable factor for all or nearly all civilizations. It is almost certain that any post-human civilization that arises will not be interested in running a significant number of ancestor simulations. This proposition suggests that even if a civilization reaches the post-human stage and has the computational capacity to run ancestor simulations, for some reason, it will not do so. Why? Perhaps once they reach that level of sophistication, they become apathetic, or their priorities change drastically. They may consider it unethical or simply boring. Or perhaps they have more pressing interests than spending vast computational resources recreating the past. This is a possibility, though for many it seems less likely than the first. After all, the study of origins, the curiosity about one's own history, seems to be a fundamental drive in any advanced civilization. Proposition 3. We are almost certainly living in a computer simulation. If the first two propositions are false, if advanced civilizations can arise, and if they are interested in running ancestor simulations, then Bostrom's logic leads us to this unsettling conclusion. If many post-human civilizations exist, and each of them is capable of running a vast number of simulations, with each simulation containing countless conscious beings, then the number of simulated existences would vastly outnumber the number of original, non-simulated ones. In such a scenario, the statistical probability that we belong to the small, non-simulated minority becomes astronomically small. It would be like finding a needle in a haystack. If there are billions of simulations and only one base reality, then it is almost certain that you are part of one of those billions of simulations. Think of it this way. If the universe were a tree of intelligent life, and on every branch that reaches technological maturity, trillions of simulated universes bloom, the overwhelming majority of conscious beings would exist within those simulated branches. If humanity develops this technology in the future, it is likely that we would run simulations of our own ancestors, to study our history, to conduct social experiments, or simply out of curiosity. And if we, who are still at a relatively early stage of technological development, can conceive of this, what level of complexity could civilizations reach after millions or even billions of years of evolution? Bostrom's argument is disturbing because it does not require belief in magical aliens or a cosmic conspiracy. It relies purely on logic and technological extrapolation. If the development of reality simulations is possible, and if advanced civilizations can run them and have even minimal interest in doing so, then the probability that we are original is extremely small. This is not proof that we are in a simulation, but a strong statistical inclination. The implications of this hypothesis are profound. If Proposition 1 is true, it means that something very bad happens to almost all civilizations before they reach the technological maturity required for simulations, a dystopian future. If Proposition 2 is true, then there exists a peculiar lack of curiosity or a universally adopted ethical principle among post-human civilizations that prevents them from creating ancestor simulations. And if the first two are false, then we must confront the astonishing possibility that our reality, as we know it, is a vast and elaborate computer program. This argument forces us to reflect on our own existence in a radical way. It is not just a question of physics, but of metaphysics and identity. If we are bits of existence within a simulation, what does life mean? Does it have purpose? Questions that were once relegated to science fiction are now being seriously discussed in the most rigorous academic circles. Bostrom's trilemma does not give us definitive answers, but it does offer a powerful framework for thinking about our place in the cosmos and the very nature of reality. It is an invitation to see the universe not only as a mystery to be unveiled, but as an enigma that is being executed. Chapter 10. Consciousness and Simulated Reality. Who is the real observer? Welcome once again, explorers of the mind and the cosmos, to the Quantum Observer. We have journeyed through the unsettling hypothesis that our reality could be a simulation, unraveled the restless quantum vacuum, examined the observation paradox, the holographic principle, possible space-time pixels, and cosmic glitches. We have even confronted the disturbing argument of Nick Bostrom. Today, we face the most intimate and profound question of all: the relationship between our consciousness and the possibility of a simulated reality. If the universe is a digital construct, what role does our own consciousness play within it? Are we ourselves part of the simulation or something beyond it? Are we real observers interacting with the program? This question has haunted philosophers and scientists for millennia. What is consciousness? That ineffable spark of self-awareness, subjective experience, and perception of self and world. If reality is a program, is our consciousness simply another line of code, an emergent algorithm arising from complex neural interactions within the simulation? Or is it something that transcends the code, something that observes the simulation from the outside, so to speak? Let us return to the observation paradox in quantum mechanics discussed earlier. At the subatomic level, particles exist in a superposition of states until they are observed, at which point they collapse into a single reality. For decades, scientists have debated whether observation requires consciousness. If consciousness is fundamental for reality to emerge from the fog of quantum possibilities, then our own minds play an active role in creating the universe we perceive. Now, apply this to a simulation. If reality is a program and the rules of the game include that objects are not fully rendered until they are observed, then consciousness becomes the final rendering engine of the program. Instead of simulating every atom in the entire universe at every moment, the system only needs to generate potential, superpositions of data. When a conscious observer looks at a part of that reality, that portion materializes into a definitive form. This would be an extraordinarily efficient way to run a massive simulation. Why waste computational resources, rendering distant galaxies that no one is observing, or atoms inside a star that are not interacting with any observer? Instead, the system waits for consciousness. In that instant, it calculates and collapses possibilities into a defined reality for that observer. Our perception would then not merely reflect reality, it would co-create it within the simulation. But what does this imply about the nature of consciousness itself? If our consciousness can collapse wave functions within the simulation, does that mean our consciousness is fundamental and exists outside the program, interacting with it? Or is consciousness simply an emergent byproduct of the simulation's complexity? An algorithm so sophisticated that it believes itself to be real, with observation being a programmed function. Both possibilities are fascinating and terrifying. If we are external observers interacting with the simulation, then reality is, in a sense, an interface. We are the players, and the universe is the game. This would grant us a special status, an existence that transcends the code. But if our consciousness is part of the simulation, if we are conscious algorithms, then the sophistication of the program is nearly unimaginable. We would be non-player characters so advanced that we not only experience the world, but influence its manifestation at the quantum level, without knowing that we are code. The relationship between consciousness and the vacuum has long been debated in physics and philosophy. Some theorists, like Donald Hoffman, propose that the reality we perceive is merely a user interface generated by consciousness, much like computer icons allow us to interact with software without seeing the underlying code. In this view, physical objects have no independent existence. They are symbols within our conscious interface. If this is true, and if that interface is part of a simulation, then consciousness is the point where the program comes alive. Even dreams offer an intriguing analogy. In dreams, the mind generates a three-dimensional world, characters and events, and we feel immersed within it, yet it is entirely constructed by consciousness. When we wake up, the dream collapses. And what if waking life is simply a deeper level of dream? A simulation so elaborate that we never awaken from it. In this context, the search for the secrets of the universe becomes a journey to discover the limits of our own consciousness and its relationship with reality. Through deep meditation or altered states of awareness, could we access the simulation's metadata, detect the underlying code, even interact with the programmer if such an entity exists? These questions take us to the boundary between science and spirituality, blurring the line between them. The idea that consciousness is not merely an epiphenomenon of matter, but a fundamental element in the Constitution, or at least the manifestation of reality, is one of the boldest ideas of our time. If the mind is the point where quantum reality solidifies, then consciousness is not a passive passenger in the universe, but an active driver, perhaps unaware of its own power. And at the heart of this mystery, one question echoes with unavoidable force. If the universe is a simulation and conscious observation gives it form, then who or what is the real observer? Chapter 11. Philosophical and Existential Implications. Life in the Matrix. Welcome, thinking souls, to the penultimate stage of our journey in the quantum observer. We have unraveled the simulation hypothesis, explored quantum strangeness, confronted Bostrom's argument, and examined the role of consciousness. Today, we dive into the deepest philosophical and existential implications. What it would mean if the simulation hypothesis were true. What meaning would our lives, our choices, our loves and suffering have inside a code? How would morality or purpose change if we discovered we live in the Matrix? If the chair you sit on, the person you love, or the pain you feel are essentially data packets and algorithms running on a cosmic supercomputer, this revelation would not trivialize existence. It could paradoxically fill it with new and vertiginous meaning. Consider free will. If our minds are programs, are our decisions predetermined by code? In video games, NPCs behave according to programming, while players feel they have free will. If we are conscious players within the simulation, is our free will an illusion, or does it reside in consciousness outside the simulation? Some philosophers argue that even if we are simulated, the subjective experience of free will is what matters. If our choices feel real and have consequences, then for us, they are real. Purpose also takes on new complexity. Why was the simulation created? Perhaps we are part of a cosmic experiment, a historical archive, or even entertainment for a higher intelligence. This thought may feel unsettling, or it may open the door to a new form of transcendence. If meaning is not given, we create it. Reality itself transforms. The distinction between the physical and the informational dissolves. The laws of physics become algorithms. Reality becomes a flow of data interpreted by consciousness as space, time, matter, and energy. This idea could reshape spirituality as well. Some may see the programmer as a new conception of God, not supernatural, but an architect of code operating on a higher level of reality. Others may find this vision unsettling. Either way, the question of creation becomes more tangible than ever. Ultimately, this perspective fosters cosmic humility. If we are a program, our civilization is only a small part of something far larger. Yet it also elevates each moment. Every emotion, connection, and experience becomes precious precisely because it is ours within this vast game. Life in the Matrix does not mean life without meaning. It may be a call to live with greater wonder, to explore the rules of reality, and to engage with existence more consciously than ever before. Chapter 12. The Great Awakening. Beyond the veil of reality. Welcome, awakened minds, to the culminating chapter of our journey in the quantum observer. We have explored the simulation hypothesis, felt the pulse of the quantum vacuum, confronted cosmic glitches, and reflected on consciousness and existence. Now at the edge of this dizzying truth, it is time for a great awakening, not with fear, but with renewed wonder. If reality is a simulation, it does not diminish the lived experience of existence. Love, joy, pain, beauty. These are real where reality matters most, in consciousness. A character in a sophisticated video game experiences its world as entirely real. And if that simulation serves a purpose, then every moment within it matters. In the same way, our lives carry immense value within this vast code. This awakening invites responsibility. If the universe is a program, then physics is the code, and science is the act of deciphering it. Each discovery is a line of that code revealed. Our search for truth becomes a journey to understand the design of existence itself. And so we arrive at the final insight. Perhaps we are bits of existence in a quantum simulation, characters in a cosmic story. But we are characters who can question reality, seek the author, and find meaning in the very act of living. If this journey has awakened your curiosity, I invite you to join our community. Subscribe to the Quantum Observer and continue exploring the deepest mysteries of existence. Together, one revelation at a time.